Okay, we are recording. So before I start talking about lecture content, exam 1 coming up Monday of next week. From what I hear, it's a good day. Why is that a good day? Because you don't have any other exams and you have the weekend to prepare for the exam. Right? That's why I hear it's a good time to have the exam. Have you guys started looking at the back exams? Have you guys started looking at the back exams? No. All right. So I have an econ test the same day. Alan, econ, come on. The video is getting recorded, so I don't want to say things, but you know exactly what I would say for an econ test. It's an econ test. Yeah. All right. There are 2 time slots for exam 1. One during class time, the other at the night, same day, 8 to 10, different exam, so 2 different versions. It's going to be proctored, so we are talking about you guys either on campus, in your room, or at home, having your mics and camera on, while your computer volume is 0, right? So your mic is on, but your computer volume is 0, so that you don't hear what is going on the channel. I'm going to be hearing all those wonderful sounds. And I will be monitoring the chat box for questions, and I will be looking at what you guys are doing. So open book, open notes. So you can have books and stuff by your side, reference sheets and whatnot, while you take the exam. You can use your laptop only for looking at the exam. So it's not like I'm going to be monitoring keyboard usage. So you can scroll through up and down. If you have a printer, feel free to print the exam. I will be sending it to you a little bit before the start of exam time. So like maybe 5 minutes before 10:30 or 8, depending on which time slot you sign up for. So you will have time to print it. So just have your printer nearby. If you don't have a printer accessible, that's fine, no problem. You can just write your answer on a piece of paper and scan it at the end of your exam. Because there are 2 time slots and it's being proctored, there are some logistical details that I would like to explain a little bit more in detail, and I'll do that this Saturday. So Saturday, 3 to 4 p.m. I've reserved, and we'll meet in the general Webex team space. I'll talk about logistics, I'll talk about the topics, I'll talk about the format of the exam, and I will take your questions after that. This will be recorded, so people who cannot make it do not need to worry. Let's see. One important thing that I'm going to tell you guys is to sign up for the time slot. So this is what I'll do. Depending on the time slot you have signed up for, I will send you guys the Webex links. So it's going to be a new meeting room. It's going to be not going to be in our regular class link. So you need to sign up to get the correct Webex invitation, and only after you join the Webex meeting, I will be sharing the exam with you. So I will be sharing the exam with you this way. I hope you guys are able to see this, at least for the people in the classroom. This is what I'm doing right now. I'm clicking on File. Hold up. Let me stop sharing here. Share screen. Yeah. All right. So if I share screen and I return to my meeting, where is my meeting? Right here. It looks like I cannot show people in the. There is a file transfer option that apparently I cannot show you guys, and it is not active while I'm sharing. So what I'll do is this: I'll stop sharing, but you guys in the room can see this, right? File and a transfer. So I'll be sending you guys the exam using this. So for that, you need to be in the Webex room. So I'll share the file this way, and then you will get it. The reason being, different people are going to have a different exam, right? Like you guys are, some people who are taking the morning exam, they're going to have a different exam. So I cannot publish it out on Grayscope, for example. We'll do a test. When we do the review, I will test this feature. I'll give you guys, not the exam, but something else. I'll send it to you. So that's called a file transfer option on Webex meetings. Have you guys used that before for any other course? I have last year. It works really well. Was that? V? Which one? Yeah, but I still like Webex meetings. The Teams interface looks very informal slash, yeah. Yeah, so I like this. So that's why I've sort of continued with this. All right, let me minimize here. Am I still recording? Yes, I'm still recording. Okay. Now, depending on how the exam turns out, I may actually increase the time. Instead of having it 2 hours start to finish, I may go 2 hours, 15 minutes or 2 hours, 20 minutes. Because sometimes the math can be a little bit time consuming, so I might extend that. So plan that for Monday afternoon, right? So if you have any engagement, you might have to sort of move that around just for, and if you have another class, let your professor know that you are going to be maybe late. So I'm hoping that it's recorded, your next lecture. So instead of ending at 12:30, you may end up at 1. Questions, concerns? Have everybody signed up for it? Yeah? Excellent. Questions for now? No questions for now? All right. So I have a question then. Oh, wait a second. There's a question here. So do we have to come to the classroom to take the exam on Monday? No, you don't have to come to the classroom. You're going to be online. Everybody is going to be online. But you are going to have your mics and cameras on. So I will also be a part of your exam experience. You will be typing in your questions directly to me using the chat box, the same chat box you're using right now. So what is on the exam and what is not on the exam? Lectures 1 through 7 is on the exam. Today, we are finishing up lecture 7. We are going to be talking about lecture 8, which is going to be on Fourier series. That is not part of the exam. Is Laplace transform part of the exam? No, because we have not talked about Laplace transform, right? Is Fourier transform part of the exam? No. Fourier series? No. Z? No. So things that we have not talked about, that are not going to be on the exam. You might think that that is very obvious, but I have had those questions in the past, which is why I am clarifying that now. So continuing our discussion on properties of systems. And this time around, we are talking about properties of systems by looking at the impulse response instead of the input-output relationship. So we are talking about how is y of t and x of t related? That was the input-output relationship. We talked about memoryless, causal, stability, Bibo stability, all of these aspects of a system, but with input-output. Now we are talking about it in terms of its impulse response. So LTI systems are bounded input, bounded output stable if you take the absolute value of your impulse response sequence, h of n. You sum up all the elements in that sequence. They should be finite. So if you have a finite sum for h of n, that is indicative of a Bibo stable system. In continuous time systems, it is simply the absolute value of h of t integrated between negative infinity to infinity. In other words, the area under h of t should be finite. If it is, then you have a Biot stable system, otherwise you don't. These conditions are actually sufficient conditions for Biot stability. Not just necessary, these are sufficient conditions for stability. So you just check for that and you will be able to comment about whether the system is stable or not. Next, the inverse of a linear time invariant system. Now, why is inverse of a system nice, something that we need to compute or interesting? Think about it this way. If I am the transmitter and if there is a receiver, between the transmitter and a receiver, there is a channel. The channel has some impulse response. If I wanted to negate the effects of that channel, then I can use the inverse of that system, right? System, inverse of that system, essentially canceling out. What that means is by designing such inverse systems and placing them in my chain after, so say this is my transmitter, this is my receiver, and this would be my channel, whatever channel I have between you and me, for example. I can find out what that inverse system is and put it in my, maybe at the front end of the receiver, or I can put it at the last part of my transmitter. I can include that in my transmitter or my receiver to negate the effects of my system, the channel, so that effects of noise are removed. The channel amplitude is increased or maintained. So all of those interesting things I can do if I'm able to compute the inverse of my system. Now let's talk about it mathematically. How do I find that out? Well, the inverse of a linear time invariant system H is indicated by H I and V, and you compute that by simply satisfying this equation. So the inverse of a system has to satisfy just this. H convolved with H inverse should give you an impulse, unit impulse, right? System convolved with the inverse of the system should give you delta. 100 multiplied by 1 over 100 is 1, right? Something like that. You're inverting the system now. And in terms of continuous time, it works the same way. H of t convolved with H inverse of t gives you delta of t. If that is satisfied, then that is, whatever satisfies that is going to be your inverse. Now, I hope right now you guys are asking this question. But what if I want to find that H, I, and V? How do I find that out? How do you think you will find that out? So here, this is a condition to satisfy. But how do I find this out? Sorry? Trial and error. So here, trial and error for signals that could be of, you can have an infinite choice for H. That means you have infinite choice for H inverse, right? So you can't keep choosing. So how would you go about finding H inverse? For this, we are not ready to have this conversation yet, but I just want to point that out. So that, go ahead. Deconvolution. Exactly right. Deconvolution. But we have not learned about deconvolution. We have only talked about convolution, right? So what is deconvolution? What is it going to be based off of? How can I do it mathematically, right? So essentially, you do this. You translate things in the time domain to frequency domain. How can you do that? Say that? Fourier transform, right? So if I take the Fourier transform of these time domain signals, on the left you have discrete time, on the right you have continuous time. Fourier transform applies for continuous time. So if I took the Fourier transform of this, and this, what do I get? H of f multiplied by H inverse of f. Convolution in time is multiplication in frequency. Yeah? So this becomes cap H of f. This becomes cap H of f inverse equals the Fourier transform of delta of t is a constant, 1. So what do you have? This is multiplication, right, in frequency. So h inverse of f will be 1 divided by h of f. 1 divided by the Fourier transform of the impulse response of the system, which is just the inverse. So you can do 1 over h of f, right? 1 over h of f, now it's like a polynomial situation. You have h of f, function in f, 1 over that, you can divide that out. What do you have to do? You wanted something in time domain. Your result right now is in frequency domain. What do you need to do? Inverse. So Fourier transform, division, inverse Fourier transform gets you h inverse of t. So we are not ready to talk about that just yet because we have not talked about Fourier transform. Before that, we need to talk about Fourier series. But that's how you would go about doing things and avoid trial and error. All right, so let me put it over here as a system. X of n goes into a system with impulse response h of n. This is the LTI system. The output is y. Y is going to be what? This is going to be x involved with h. And if that goes into another system, h inverse, you should get back the same thing that you sent. Transmitter equals receiver. Effects of channel canceled out, right? So that would be x of a convolved with h convolved with h inverse. That should be x. Is it? Yes. Why? X, h, h inverse. H inverse convolved with h inverse, we know it should be delta, right? So if this should be delta, then that is going to be x. Whether it is n or t, doesn't matter. One case it is discrete, one case it is continuous. Questions here about inverse of a system? The conditions it should satisfy, and essentially talking about how would you do it in the future. We are not ready to do that just yet. Does the system have to be stable to have an inverse? You can have an inverse of the system. The check for stability is independent of whether the system is stable or not. Something that is, if you are still able to find the inverse mathematically, it may or may not be stable. So they are not related. Step response. We talked about impulse response. Impulse goes in, impulse response comes out. Step response, step goes in, step response comes out. And because there is a mathematical relationship between unit step and an impulse, what is the relationship between unit step and an impulse? Derivative of a unit step is an impulse. In other words, you integrate impulse, you get unit step, right? So there is a integration differentiation relationship between impulse and unit step. Hence, the same applies for the response, the impulse response and the step response. So in order to compute the step response and relate it to the impulse response, we need to do a little bit of math. This is going to be quick. U of t goes into an LTI system. With an impulse response of h of t, you get y step. Why? Because we are talking about the output when the input is step, and we are denoting that as y step of t. And you know what this is going to be, right? This is going to be simply be u of t convolved with h of t, right? Unit step convolved with the impulse response of the system. Now, this is continuous time convolution. I can express that using convolution integral. So there it is. Y step of t is integration negative infinity to infinity, u of tau, h of t minus tau d tau. Why did I choose u of tau? Because I want that to be a 1, and I don't want there to be a t in there. So because u of tau is only valid when tau is greater than 0, I can adjust the lower limit of the integration to be a 0. Upper limit stays at infinity. It's going to be 1 multiplied by h of t minus tau remains as is d tau. Guys, okay with that so far? We have simply adjusted the lower limits because of the presence of u of tau. Now we do a change of variable. The change of, I just want one thing over here, right? Why do I want only one variable over there? Because I want to say like I said, step is an integration of impulse. I want to be able to say step response is going to be an integration of impulse response. But that impulse response should have some h of t dt, right? Something like that. Right now it has two variables. So I'm going to apply that change of variable to get there. Change of variable, t minus tau is equal to v. D tau becomes dv, negative dv. I need to evaluate my lower limit and upper limit. Upper limit over here, lower limit over here was tau equals 0. So when tau equals 0, v equals t. And when tau equals infinity, put infinity over here, t minus infinity equals v, so v equals infinity. Right? So for negative infinity, so 0 to infinity will become t to infinity. Because you have d tau equals negative dv, d tau equals negative dv. Now you have negative, the integration is from t to infinity, hv dv. And because you are integrating from t to infinity and you have that negative sign, you can simply consume that in your integration and say, integration is going now from negative infinity to t, hv dv. What is that? Integrate the impulse response starting from negative infinity to some arbitrary stopping time t. Integration of impulse response is the step response. That's what we have proved. And because of this relationship, consequently, we have this relationship. Impulse response is the derivative of the step response. So if I tell you the step response, I have told you the impulse response. And if I have told you the impulse response, I've told you everything about the system. So on the exam, this could happen. I may ask you guys to find out the response of a certain system. You are given the input, but I may characterize the system not using the impulse response, but using the step response. So you guys need to say, all right, I now have the step response. I'm going to differentiate it, find the impulse response, then use it in my convolution to find the output of the system. Or things like this. You can do a lot of questions with just this idea. Step response is what? The output of the system when the input is step, right? Do you guys agree with that? When the input is step, the output is the step response. So let us assume that I give you guys the step response. I can easily ask you something like this. Here, this should be, let's see if you guys can make this jump. You are given y step of t. You are given the step response there, right? And you are asked to find something like this. X of t equals u of t minus 3 minus u of t minus 5. What would be the output to that? LTI system, of course. System is LTI. You are given the step response. You are given the input, find the output. What would that be? Let me make it a little bit more interesting. 2, 5. You're given the step response. Would that be necessary? Derivative? So here, you already know the step response. So you know something like this, right? U of t, y step of t. You already know this. You already know that, right? Now you need 2 u of t minus 3 minus 5 u of t minus 5. What would that be? 2 y step of t minus 3 minus 5 u of t minus 5. Not u. Not even, you don't even need to evaluate the impulse response. You can just go by this. You guys see why this works? Yeah? Superposition, right? They found me. All right. Now, let's try to do the same thing. for discrete time systems. So for discrete time LTI system, the step response is going to be the convolution of unit step with the impulse response. We have essentially said the same thing as this, except we have written it for discrete now. U of n convolved with h of n can be expressed using convolution sum. M equals negative infinity to infinity, h of m, u of n minus m. U of n minus m, n minus m has to be greater than or equal to 0 for it to be a 1. So put that into condition. This is going to be 0 when n is less than m. It's going to be 1 when n is greater than or equal to m. That will help you adjust your lower limit of the, not the lower limit, upper limit of the summation. Y step is going to negative infinity to n h of m, adding up all the elements in the impulse response from negative infinity to some n. Whatever n you stop at, that is going to be your y step of n. Right? Y step of 2, stop at 2. Y step of 3, stop at 3, and so on. Now, if that is your step response, what is the impulse response? You see, this one is accumulation of everything until n, right? So if you want impulse response, then at n, what do? Take this, subtract this, right? Take that, subtract that, you get that, h of n. So h of n is y step of n minus y step of n minus 1. You can also prove this by doing this. You can say, this is y step of n, rewrite the same equation for y step of n minus 1. What is going to be y step of n minus 1? M from negative infinity to n minus 1, h of m, right? Write those two summations, subtract them. What are you going to be left with? H of n. We did, but that was impulse and unit step. Now it is impulse response and step response. So that was, we did this in, I think, lecture 4 maybe, where we were trying to find out the relationship between u of n, r of n, and delta of n. This is a relationship between their responses. So step response and the impulse response. Similar relationship, actually. Yeah. Questions here? Oh, sorry, what? Oh, yeah. All right. Let's move on. And since you guys have been missing circuits, I thought I will put in some circuit thing in here. Very simple RC circuit. R is 1, C is 1. 1 ohm and 1 farad, right? So innocent. So what we are going to do is we are going to try to find the impulse response of an RC filter. Impulse response of an RC filter where R is 1 ohm and C is 1 farad. I'm going to need, because I'm saying that this is an impulse response, I'm going to call this a RC filter. That's my system. So what's my input and what's my output? Well, my input is x of t, that's my input voltage. And y of t is my output voltage across the capacitor. Right? So I'm using input and output as voltage waveforms. R and C are my two elements. That's it. And I'm talking about the current. Current through the resistor is small I. So let's try to use some circuit analysis techniques here. The first one is the current voltage relationship of a capacitor. What is that? I equals C dV by dt. Right? You guys have heard this, seen this so many times. It just rolls off the tongue, doesn't it? C dV by dt, L di by dt. Current through the capacitor equals C is 1, so that's 1, dV by dt. Voltage across the capacitor is y of t, so dy by dt. Yeah? Next, KVL. Voltage of a loop equals 0. Algebraic sum of voltages in a loop. X should equal I times 1 plus Y. Right? Input voltage should be equal to the voltage across the resistor plus the voltage across the capacitor. X equals I times 1 plus Y of t. You combine those two, you get a differential equation. X of t equals y of t plus dy by dt. Input equals y of t plus the rate of change of y of t. Now, let us assume that our input is a unit step. X of t is u of t. If x of t is u of t, can I say y of t is y step of t? That's just the way of saying when the input is unit step, the output is the step response. So I'm going to assume that. Next, instead of using x here, I will use u. Instead of using y here and here, I will use y step. So I'm essentially substituting that condition for unit step and the step response in my circuit ODE, ordinary differential equation. Once I do that, I get this. X of t, u of t, equals y of t, y step of t, plus dy of t, dy step of t. Right? So far, so good? Next, I have a function, I have the rate of change of that function, and that should equal unit step. Right? Function plus the rate of change of function should be the same function then, if I want to make that into a zero. What function do I need to use here? Exponential. If I use an exponential, its derivative is also going to give me an exponential. So I'm going to, well, the initial condition over here I'm going to assume is that the step response at time 0 is 0. So the response of the system, there's no initial charge on the capacitor essentially. I'm going to multiply this particular equation by e to the t, the same thing that you guys have been doing in your DFQ course. You multiply e to the t throughout, what do you get? E to the t y step, which is here. E to the t rate of change of y step, which is here, equals u of t. I'm just writing that as e of t. I've removed the u of t. I've simply written, instead of writing e to the t u of t, I'm writing e to the t. I'm going to include that u of t later on in my answer. Now look at this. What is that? E of t function plus e of t rate of change of function. That is simply rate of change of e to the t y step of t, right? Product rule of differentiation. So rate of change of this function equals e of t. That's where we are at. Now when you integrate both sides, what are you left with? You are left with e to the t y step of t on the left side, and you integrate e to the t on the right side. If you are integrating e to the t on the right side, what are you going to get? Well, e to the t plus the integration constant, c. I'm going to use the initial condition to evaluate c. Evaluate this guy for time equals 0. What do you get? C equals -1. I'm simply taking the circuit, using circuit analysis technique to come to the differential equation, assuming a input-output u of t y step of t, plugging it into my differential equation of the system, trying to solve that ordinary differential equation, using the initial condition to find the integration constant. That's what I've done so far. With this, what do I have? I have this. E to the t y step of t equal, oh, where did you get the e to the t from? I have simply chosen it to multiply it because I know that with exponential functions, when I differentiate them, I get back the same exponential functions, right? Because I need something like this, y of t plus dy of t. That should go to a constant. Because of that, I'm multiplying it with e to the t. So where did I get it from? Sort of a manipulation technique for differential equation solve. Next, e to the t y step of t equals e to the t minus 1. That's what we had after the initial condition. Divide e to the t throughout, you get y step of t, step response equals 1 minus e to the minus t u of t. You guys agree with that? Step response. Think about the step response of an RC filter. This is the step, right? Let me try it in red. This is the step, right? The step response is what? Yeah. Next, we know that to find the impulse response, all we need to do is differentiate the step response. If you take this guy and differentiate it, what do you get? Differential of this, which is e to the negative t u of t. impulse, the output will be there, impulse response. So I think with your circuits, you guys have talked about how to find the output of these RC, RLC, single first order or second order circuits with the math, right? Ordinary differential equations, substituting initial conditions to find out y of t, the output, whether it be current waveform or the voltage waveform. Now you're thinking about it in terms of systems. That's all you're doing. You're thinking about it in terms of what is the system here? How can I characterize it as an impulse response? Once I do that, once I find out the impulse response, now I don't need to ask you, I don't need to say anything about that circuit. You have the impulse response, which means that any new input I give you, you will be able to tell the output. You will be able to compute the output. Questions? Good. So there is a u of t over here. There is a e to the minus t u of t over there, right? So when you differentiate this guy, you again need to use the product rule. So you get what? E, you're differentiating e to the t, because you're going to differentiate even this guy, right? When you differentiate that guy, you get delta of t, scaled. You can check. I think the math will cancel out for that. All right, so exam 1 is going to be until here. We are going to be talking about Fourier series next. Let us try to make this a little bit more interesting than it may appear. So let me spend time talking about why we need to talk about Fourier series. What are Fourier series? And then give you guys some motivation to think about Fourier series, essentially. That's what I want to do. Why are we worrying about Fourier series? That's the question. So suppose I have any point in a two-dimensional space, right? I have a two-dimensional space. I have an x and a y axis. Let's say I have three-dimensional. I have a point in 3 dimensions, x, y, z. If you want to represent that in 3 dimensions, what do you do? As a vector, how do you represent a vector in 3 dimensions? Matrix, so just think vectors. Don't even think the math that supports that. Think vectors. If you want to represent that a particular point in 3 dimensions, can I say that I will need to project that point onto x? I get some projection on x. I get a projection in y, and I get a projection in z. All these projections multiplied by their unit vectors added up will give me the point. Can I say that? Project it on x, project it on y, project it on z. Forget about projecting on 3 spaces. Let's do 2. If you had a point, how can I find this guy? Project this guy on x, project this guy on y, add those up, you get the point. Do the x and y have to be perpendicular? X, y, z, perpendicular, right? X, y, perpendicular, orthogonal functions. X, y, z, again, orthogonal functions. So what are you doing? You are projecting the point onto all the orthogonal functions that make up the dimensions. 2 dimensions, it's x and y. 3 dimensions, it's x, y, z. How many ever dimensions they are, you're projecting that point onto each of the orthogonal functions. Those are going to be your projections. Once you take those projections pointed in x, y, pointed in x, y, z, and add them up, you get back your signals. Yeah? We are going to do the same thing, but with respect to real signals now, with periodic signals. We are going to project signals onto complex exponentials. Complex exponentials that have a particular frequency, fundamental frequency, or they may have integer multiples of that fundamental frequency. Second harmonic, third harmonic, and so on. Once we project that, we get the projection onto a particular orthogonal function. You take all the projections, multiply it with their magnitudes, and add those up, you get your periodic signal. So when we were breaking up in the last class, at the end, I said, hey, you have this square wave. How are you going to represent that using sinusoids? That's what we were doing. We were taking each sinusoid. What does a sinusoid have? Sin x. You can express that in Euler's, right? Or in other words, you can express this. What is e to the ix? What is that? Thank you. I don't know what happened there. A physicist woke up. All right. So each complex exponential that we have is a sinusoid with that same frequency. So those are going to be my orthogonal functions. I'm going to project my signal, x of t, y of t, whatever it is, a periodic signal, onto complex exponentials. And I'm going to find all those projections. Their amplitudes are going to be my Fourier series coefficients. As simple as that. We'll sort of dig deeper when we get into it. But in order to talk about Fourier series, essentially the coefficients, right? Those coefficients, what should be the strength of the second harmonic? What should be the amplitude of the fourth harmonic, third harmonic, fundamental? To answer all those questions, that's here. We need to be able to do these two things. One, find the response of linear time invariant systems to exponential inputs. And exponential inputs is something that we love. Why is that? Because exponential signal goes into an LTI system, the output is also an exponential function. Input exponential, output is exponential. The only thing that changes is the amplitude of that exponential. That's it. It's a very nice, and you can sort of prove that using the convolution integral as well. So we'll try to find the response of exponential inputs first. What can we do with the complex exponentials? We can make up an orthogonal set. Why do we need an orthogonal set? I need an orthogonal set so that I can take any signal and project it onto all the orthogonal functions in that set. So I need an orthogonal set. I'm going to make up my own orthogonal set, which comprises of complex exponential inputs. So you see how we are doing here. First, we are trying to find the response of LTI systems to complex exponential inputs. Next, we are trying to express all the signals in orthogonal sets like using complex exponentials so that we can answer the Fourier series, which is to make up a periodic signal using projections of all those orthogonal sets, orthogonal functions in a set. The orthogonal functions being complex exponentials. If you have got a little bit of that, that's fine. Even a little bit, that's okay, because we're going to spend time talking about these things. Response of LTI systems to complex exponentials. Why are they important? Why are complex exponentials important? This is the reason. The response of an LTI system to a complex exponential input is the same complex exponential. E to the st goes in, e to the st comes out. The only change is it will have a h of s, some eigenvalue, some amplitude change. That's it. A function goes in, e to the st, where s is your Laplace variable here, complex function, sigma plus j omega. Output is h of s e to the st. Right now, you might be thinking, oh my gosh, Laplace is coming. It's not. We are far away from Laplace. We are going to be talking that after Fourier transform. We are just using Laplace variable s here to talk about the orthogonal set. So e to the st goes in, where s is a complex variable. H of s, that is what? H of s. Can somebody tell me what is H of s? Think about these questions. Why did he use the letter H? And why is the parameter s? What is it? Good. Okay, so think about it like this. You close your eyes, you open your eyes, you are in circuits class. What is H of s? Transfer function. There it is, right? So you're either your transfer function or your, if you were in the Fourier transform world, it would be the frequency response, right? So either the frequency response, and in this case, H of s, that's your transfer function. So H of s evaluated at that same s, right? The same s here, multiplied by e to the st. So that's nice, right? Whatever, so here, think about it like this. Any LTI system, if I give it an exponential input, the output is exponential, the same exponential. The only thing is the strength of it is changing, right? Isn't that like, for me, it's not very intuitive. It's not very straightforward. So for example, e to the 2t goes in. What comes out? Right? E to the 2t goes in, evaluate the transfer function at s equals 2, multiplied with e to the 2t, where h of 2 is your eigenvalue to the function e to the 2t. And this is not for a specific system. This is for all LTI systems. So that proof is going to be pretty simple using the convolution integral. You can consider an LTI system. We are going to represent the impulse response of that system using h of t. And we are going to apply this special input. What is that? E to the st, where s is representing a complex frequency variable. So if x of t is e to the st, goes into the LTI system with impulse response h of t, the output can be computed by convolving input and impulse response. E to the st convolved with h of t. Convolution integral comes in. Y of t is integration negative infinity to infinity s tau h of t minus tau d tau. Or because it is commutative, you can write it as h of tau e to the s t minus tau d tau. Switch it around. Next, e to the st is independent of tau, right? This guy is independent of tau. So you can pull it out of the integration. Whatever is left is what? H of tau e to the negative s tau d tau. All of that. That is h of s, the double-sided Laplace transform, or whatever we called it. We called it what? Transfer function of a system. Right? That's defined as h of s. So when the input is e to the st, your output was e to the st multiplied by h of s. H of s being the eigenvalue of the function e to the st. Complex exponentials are eigenfunctions of LTI systems. That's what it boils down to. So complex exponentials, so all of this to say, I could have picked any orthogonal set, right? To project my signal, I could have picked any orthogonal set, xy, xyz, any orthogonal set. There are some mathematical conditions that need to be satisfied. What are they? They are that any signal has to be orthogonal to every other signal in that set. That's the only criteria. And a number of functions will satisfy that. But we are, for LTI systems, we are going to consider complex exponentials because they are the eigenfunctions of LTI systems. Questions so far? Proof was simple, right? Nothing, it's just h of s. You guys have seen Laplace transform, like a little bit at least. maybe in differential equations, circuits definitely, yeah. So everybody agrees to the formula at least, right? To find out the Laplace transform of h of t, which is h of s. How do we denote that? We denote it like this: h of t Laplace transform h of s. And that is the equation. Next, let's try to build on this. Once we have proved it now, let's build on it. If the input of the system is e to the st, then the output is e to the st convolved with h of t, which is eigenfunction, eigenvalue, eigenfunction, e to the st, h of s. Now, let's try to build on that. Let us suppose my input is a1 e to the s1t plus a2 e to the s2t. Can you quickly review? All right, that's a big, so here, think of eigenvalues as the projections of a signal on the eigenfunctions. A1 and A2 over here are belonging to the set of complex numbers. A1 is complex, A2 is complex, S1 and S2 also are complex. They are just complex variables representing the frequency. If this is the input, then what is the output? Anyone want to take a shot? What is y of t going to be? It is an LTI system. Two transfer functions. This is just h of t, right? So there is going to be h of s, but we are going to evaluate that transfer function at s1 and then s2, right? So I've got what? Y of t equals a1 cap h of s1 e s1t, yeah, plus a2 h of s2t, h of s2 e to the s2t. Now, once you do this, can we maybe attempt this? Earlier question was, what if you had two complex exponentials? Now the next question is, what if you have infinite complex exponentials, starting from 1 going to infinity? ai s sub I t. That's my input. a1 s1t, a2 s2t, a3 e to the s3t, so on up to infinity. What would be the output? We already did this for this. So can we maybe write, go ahead. So can I use the same I is infinity, infinity? All right. AI, is that okay? SI, good. Now look at this. If I'm able to represent any periodic signal in this fashion, scaled summation of projections of complex onto complex exponentials. So complex exponentials can make up my orthogonal set. I can find out what are those. Once I have figured out my orthogonal set, I can project the signal onto those infinite complex exponentials, and each of those are going to be what? A1, A2, A3, and so on, the coefficients that go in there. And I will be able to find the output for those. Right, let me say that again. If I wanted to find out the output of any LTI system to any periodic signal, square wave, triangular wave, ramp function, and so on, I can do this. I can represent that periodic signal using projections on its orthogonal functions, and I'm using complex exponentials as the orthogonal set. Once I'm able to do that, I'm able to find out the output for those things. All of this to say, if I was successful in representing any periodic signal using complex exponentials, then I know the output for an LTI system for that input, right? So with this, I'll be able to find out the output of LTI systems for periodic signals as the input. Yeah. All right. So next, our goal is going to be this: decompose periodic signals into a summation like this. A point, project on X, project on Y, add them up. I get the signal, right? When you are projecting it on X and when you're projecting it on Y, you are essentially decomposing it onto the orthogonal set. That's what we want to do here. Complex exponentials are our orthogonal set. We are going to decompose our input X of t into those infinite orthogonal functions. So let's talk about orthogonal set of signals. Suppose you have a set f1, f2, f3, and so on up to fn. These are n functions. This is going to be considered as an orthogonal set if it satisfies this particular criteria. And it is orthogonal for a specific duration of time, 0 to cap t. So all it has to satisfy is this integration. Has to be a 0 when m is not equal to n. So you take any signal with any other signal and you apply this integration. What is this integration? Let me talk about that. Here you have one function. This is multiplication. Here you have complex conjugate of the next function, right? This is complex conjugate. So take a function, take the complex conjugate of the another function, multiply them, integrate it for the time that you are trying to evaluate whether they are orthogonal or not. And if that evaluates to a 0, when m doesn't equal n, that is going to be orthogonal. Those two are orthogonal. And if that, suppose they are equal, fm conjugate, then that will evaluate to the energy in that signal, fm. That is going to be a finite value, em. Because what happens when you do this? fm conjugate, what happens then? It becomes magnitude squared, right? Complex conjugate multiplied, it becomes magnitude squared. So that's going to give you the energy in that mth function. So if this is satisfied and if you start seeing zeros over here, you know that that is going to be an orthogonal set. Right now we are talking about n signals that could belong to this orthogonal set. One such example is this. We are conveniently going for a set of signals, set of functions that are complex exponentials. You see, you hear the term complex exponentials a lot. Why is that? On one hand, you have an LTI system whose eigenfunctions are complex exponentials. On the other hand, you have, hey, if I'm able to prove that orthogonal complex exponentials make up an orthogonal set, then I will be able to find the response of each of them or a bunch of them summed together because it's an LTI system. So consider this particular set of functions, right? You have what? You are going to negative infinity on this side. You are going to positive infinity on this side. What do you have in the middle? Over here you have 1. Then you have e to the j omega t, e to the j 2 omega t, e to the j 3 omega t, and so on. It's a complex exponential DC, right? No frequency, fundamental, second harmonic, third harmonic, fourth harmonic, and so on. You have integer multiples of omega naught. What is omega naught? Omega naught is the radiant frequency of the periodic signal that you were trying to decompose. Square wave. Decompose the square wave. The square wave will have some time period. With that time period, you can find out if you have the time period, you can find out f naught. With that, you can find out omega naught, right? So suppose you have a square wave. you can project that square wave onto a constant, onto the first harmonics, onto the second harmonics, and so on. All you will need to find is, after you project any periodic signal onto this set, what is the magnitude, right? What is the magnitude of the fundamental? What is the magnitude of the second harmonic, and so on? So at the end, you will be able to answer something like this. A square wave is made up of a bunch of sinusoids, right? So what sinusoids should I choose, and what is the strength of those sinusoids to add up, right? It turns out for a square wave, all the even harmonics are 0. A2, A4, the coefficients of the second harmonic, fourth harmonic, sixth harmonic, all the even harmonics are 0. You only get odd harmonics, 1, 3, 5, and so on. So over here, I'm just taking the first 6 harmonics here. So essentially, I'm taking the DC value, plus and minus 1, plus and minus 3, plus and minus 5. That's it. If I take plus and minus 1, 3, 5, and add up, I will, you see how close I am to the square wave. And I can get closer and closer as I include more and more harmonics, 9th, 11th, and so on. So what are you trying to answer? With respect to the sinusoids, what are you trying to answer? Only 2 questions. What is the frequency of those sinusoids? What is the amplitude of those sinusoids at those frequencies? Right? Frequencies are what? Plus or minus 1 omega naught, plus or minus 2 omega naught, 3 omega naught, 4th harmonic, 5th harmonic, and so on. What is omega naught? Well, you know the time period. You invert the time period, you get f naught. You do the 2 pi f. 2 pi f is what? Omega. So if you know f, you multiply by 2 pi, you will know omega naught, right? So you know omega naught now, which means you also know plus or minus 1 omega naught, 2 omega naught, 3 omega naught, and so on. How do I find out the amplitudes? Well, take the square wave, project it onto the exponential e to the minus j2 omega naught or plus j2 omega naught. Whatever projection you get, that's going to be the strength of that. You see that? You see that how we are decomposed? What our goal is here? A little bit. All right. Let's do better with this. All right. So here, that's our goal. Eventual, like end goal. But we still haven't proved that this is an orthogonal set, right? We still don't know whether this is an orthogonal set or not. So let's try to prove that. Let's try to see if this actually meets this criteria. This is an orthogonal set. So the claim is, yes, it is an orthogonal set with any omega, for any omega naught, where the time period of that periodic signal satisfies this. T equals 2 pi divided by omega naught. So once you know the time period of the periodic signal, then you know the fundamental frequency, which is 1 over t, and then the fundamental radian frequency is going to be what? 2 pi f0 will give you omega naught, which is simply going to be 2 pi divided by t. We are doing this for periodic signals. Let's try to see if that complex exponential, set of complex exponentials makes up an orthogonal set or not. Let us try to see. When m doesn't equal n, you should be able to take any complex exponential from the set and multiply it with the complex conjugate of any other complex exponential from the set. Right? 0 to t, e to the j m omega naught t multiplied by e to the j n omega naught t conjugate dt fm fn complex conjugate. Complex conjugate gives you a negative over here that is included over there. You have e to the j m minus n omega naught t. Should be pretty straightforward to integrate a complex exponential. You got an exponential here divided by whatever was in the power of the exponent. Integration from limits stay the same, 0 to cap t. Right? You're evaluating that integration over one time period. Integrate, substitute the limits, simplify, you will see that this goes to 0. Because the numerator is 1 over here, 1 over here, because what is that? M minus n 2 pi. What is m minus n? Is m an integer? N an integer? M minus n will be an integer. Integer multiples of 2 pi. 0. Integer multiples of 2 pi j. E to the j multiplied by an angle which is an integer multiple of 2 pi. What is that? 1, right? All right. So here, I think this sort of cosine. No, let's not do that. Let's do this. E to the jx is what? Plus or minus cosine x plus or minus j sine x, right? If this x over here is an integer multiple of 2 pi, what are you going to get? Cosine integer multiple of 2 pi, 0, right? So 1. Can I see that? So that will be a 1, that will be a 1, so it will evaluate to a 0. Now, since we are talking about Euler's identities, let us also finish talking about the other two. All right, cos x. What is that? E jx plus E minus jx divided by 2. That's okay? Next, sin x. E minus E. Is that okay? Oh, no. You guys are simply believing me. Don't do that. No, it doesn't. What is that? No, no, no. We don't need to do that. I missed something here. What is wrong with this? There's extra j in the bottom, right? Well, I was just trying to see whether you guys are in or not. I just used it many times. Let's move past that. All right. So what are we doing next? Well, when m is not equal to n, we have proved that the complex exponentials give you that 0 result. So that's good. How about when m equals n? When m equals n, you have e to the j m omega naught t multiplied by the complex conjugate of the same thing. You get m minus m, 0 for the exponent, so 1 dt, just t. That would be the energy of that complex exponential. M over here belongs to a set of integers. N over here belongs to the set of integers. When m equals n, we are talking about the same signal, e to the j2 omega naught t, same one. When m is different from the next, we're talking about e to the j2 omega naught t with e to the j3 omega naught t. Questions about this proof? So I hope everybody agrees now that this is satisfying this condition, which means it's an orthogonal set. So we have got the set of orthogonal set. All we need to do is project our periodic signal onto each of those functions. Let's project x of t onto this guy, and this guy, and this guy, and this guy, and this guy, all of them. When we do that, we are going to get our complex exponential coefficients. Later, we will call them Fourier series coefficients. A little bit too much math? All right, so here, only 20 more minutes of this torture. And this is a little bit dry, so I'm trying my best to get done with this. Hopefully after the exam, you guys don't have to come back to this. All right, so approximation of x of t. X of t is what? Periodic signal. Let's try to approximate it or get as close to the square wave as possible by finding out those projections. We can approximate a signal x of t using the orthogonal set. We are talking about the n signal orthogonal set. Later on, we will stick to the orthogonal set of our choice. What is that? Complex exponentials. And we are going to look at it for its one time period, 0 to t, fundamental time period. What do you do with the projections? Project it on x, project it on y. Take the projection, multiplied by the unit vector, plus take the projection, multiplied by the unit vector, add those up, you get the point. Yeah? X of t can be represented, approximated as, if you have 1 to n, what are those? N signals. You project f of n are your unit vectors. Cn are the projections on those unit vectors. Projection multiplied by the unit vector plus projection multiplied by the unit vector plus, and so on. You include the complete orthogonal set, you get back your signal x. That's how you're decomposing x. You need to stick with, you need to have a choice for f, right? Which belongs to the set of orthogonal set, which belongs to a set of signals in the orthogonal set. And now we need to find Cn, the coefficients. So let me ask you this. In words, can you guys tell me, how will you find Cn? There are a few ways to find Cn. Let's talk about two things. One, what will be your approach? Two, what are you trying to optimize? What are you trying to improve after you select Cn? The way you do it, and this is sort of, have you ever heard of Gram-Schmidt procedure in your math classes? Maybe a little bit? Gram-Schmidt. No? Gram-Schmidt, okay. So Gram-Schmidt is this. Take the signal x, project it on x, right? Whatever remains, project it on y. Whatever remains, project it on z. That's it. So you take the signal, project it on one orthogonal function. Whatever remains, you put it on the next one. Whatever remains, you put it on the next one. That is how you find out all those coefficients, C1, C2, C3, for the signals F1, F2, F3, and so on. So you project the whole signal on x. Whatever remains, you project on y. Whatever remains, what you project on z, and you continue. In our case, what will we do? We will take those coefficients. What are the orthogonal set? E to the j omega naught t, e to the j2 omega naught t, e to the j3 omega naught t, and so on. And you also have it on the minus side. Those are your functions. You take the signal x, project it on one. Whatever remains, you project it on the next one. Whatever remains, you project on the third one, and so on. So that's what you're trying to do. That's how you evaluate Cn. But in all of this, you're trying to minimize what? You're trying to minimize the error, right? X of n, you should choose Cn such that x of n should be as close to this guy as possible, right? You're choosing those, because this is set. For us, this is the set of complex exponentials. That's set. We are trying to find this. And we are trying to find this such that our square signal is as close to that squiggly signal as possible. That's how we are trying to find Cn. We are trying to optimize that. All right, so error in the approximation. What is the error in the approximation? True signal, square wave, minus the sum of all of these, right? That's your error. We are trying to minimize that. How can you minimize that? The coefficients Cn, the projections on each of those n signals, should be selected such that the energy Et is minimum. Again, why didn't I say Et is minimum? Why did I say energy in Et is minimum? This goes back to, I think, the first lecture or second lecture. Go ahead. No. So it's not because of complex or real. It is because of the sign, right? So if error is positive, then how about negative? Well, you don't want it to be positive or negative. You want the energy in E of t to be minimum, right? So that's why we do a minimum squared error. We don't do we do MSE, right? You guys have heard the term MSE or LMMSE. MSE is minimum squared error. You design filters or you design systems so that your error is minimized in terms of its square, not just minimized. MSE, you have heard MSE, minimum squared error? All right, if you have not heard it in your 4000 level classes, you will for sure hear it. Yeah, so okay, coefficients should be selected such that your energy is minimized. Next, energy in E of t. Let us denote that by this, cap E sub E, that's energy in the error signal. How can that be evaluated? I'm evaluating that from 0 to t. I said energy, so I'm doing a square of the energy signal, square of the error signal, dt. I had earlier computed error, true signal, the periodic signal, minus the sum of all its projections, right? That was the error. Square that, and that's how you find out your, this is E, and that's your square. So let's try to break it up into three things. X squared, y squared minus what? 2xy. So you have got x squared over here, you have got y squared over here, you have got 2xy over here. The first piece is what? Energy in the x, Ex, energy in x. Doesn't matter what Cn is, right? Like Cn doesn't play a role over there. This guy, yes, negative 2x of t is there, Cn is there, Fn is there. But when you integrate with respect to time, the only things that have time, the functions in the orthogonal set and our x of t, the signal that we are trying to decompose. The last one is going to be what? Cn squared and then square of these signals, Fn. Earlier, we said this is orthogonal set. And if n equals m, this should give you energy in that. So this is En. Yeah, so that's coming from this guy. When n equals m, this multiplied by that is going to give you the square, and that will simply be the energy in the mth signal. We are talking about it nth signal now, En. So you have got E, energy in the error signal, equals Ex, energy in the x of t, the signal that we are trying to decompose, minus 2 times this summation over all the dimensions, coefficients multiplied by 0 to t, Fn, x of t dt, plus that. This is coming from summation Cn squared En, that. Next, this guy depends on Cn, this guy has a Cn, but this guy doesn't have a Cn. How is the optimal choice of Cn going to be? Well, we have to choose Cn such that the derivative of this energy of the error signal with respect to Cn should go to 0. That's how we optimize functions. We find the derivative and let them go to 0. Slope at that goes to 0. That's how you find out minimum. So when you do that, you see, because you are differentiating with respect to Cn, this goes out, you will be only left with these two guys. So you'll be left with negative 2 times integration 0 to t, Fn of t, x of t, plus from this guy, when you differentiate it, you get 2 Cn En equals 0. Cn can be now written by rearranging this as 1 over En integration of 0 to t, x of t, Fn of t dt. So here, think about this. Coefficient of any projection, any nth projection, coefficient of the nth projection can be computed by 1 over En, where En is the energy in that nth orthogonal function. Integrate 0 to t over one time period of x of t. The signal itself multiplied by each orthogonal set, each orthogonal function dt. How is it going to change for us? We are going to, instead of calling them CNs for coefficients, we are going to call them Fourier series coefficients. We are going to call them AK. Instead of Cn, we are going to call them AK, Fourier series coefficients. And what are the Fourier series coefficients going to be over here? Fn, it is going to be your e to the j plus or minus k omega naught t. You see this? Kth coefficient, kth orthogonal function. X of t is going to be x of t. And this guy, tell me what this guy is going to be. En for complex exponentials. We have found that out. T, right? When we were doing that proof for complex exponentials, we found the energy in that to be T. So what you will see later on is AK equals 1 over T, 0 to T, x of t, e to the minus j k omega naught t dt. That will be how you will find out the Fourier series. Go ahead. Oh, I'm sorry, I didn't get it. Is that a little bit like sine? Yes, so there are two very similar. So first we'll talk about the Fourier series coefficient, Fourier series, which is complex exponentials. Then because a complex exponential is also related to cosine and sine, that we are going to call that by a different name. We are going to call that trig Fourier series. So that's sort of at the next stage. Let's see. Is it helpful if I call these, if I name them here? Cn, what should I call Cn? Coefficient of nth projection. No, I shouldn't say that. Coefficient of projection on nth orthogonal function. En, energy of nth orthogonal function. T is one time period. Fn. Fn is what? Nth orthogonal function. Because this was a general case, right? We said F1, F2, F3. This was not a specific case. Our specific case will be complex exponentials. So we are going to refer to those as AKs and e to the jks. So another point I would like to make is, most books I've seen, there's a usage of AK for Fourier series coefficients. It's AK, but in some it is Cn. So sometimes it's Cn. Mostly I like to use AK, but sometimes if you see Cn, C1 is the same as A1. Kth coefficient versus nth coefficient. Questions? Okay. So we talk about exponential Fourier series. Our Fourier series coefficients are going to be different now. So the exponential Fourier series is defined by this. X of t, which is a periodic signal, can be represented as a summation of Fourier series coefficients multiplied by those complex exponentials. Where is this coming from? This box, where is this coming from? Well, if I go back and show you the general case, right here, you see this x of t, this was an approximation, 1 to n. Now we have made it negative infinity to infinity, so we are including everything in that signal. Cn become ak, Fn became our complex exponentials, right? That's how we are able to go to exponential Fourier series. Omega naught is the fundamental frequency, which is equal to 2 pi f0. Time period is cap t. T and omega naught are related. T equals 2 pi over omega naught. X of t is your periodic signal. If a signal is periodic, then it has to obey this criteria. X of t should equal x of t plus cap t, where t is the minimum time period for which this is true, because this will obviously be true for 2t, 4t, 3t, and so on, right? So cap t is the minimum time period for which this is true. So here is the question. What all can you do with this? One thing is set. The complex, the orthogonal set is, function is set, right? E to the j k omega naught t is set. K is an integer, 1, 2, 3, 4. E to the j k omega naught t. So if you know the time period of the periodic signal, you know t, you know f0, you know omega naught. So this guy is set. This guy is your square wave, so that is set. The only thing that you will need to find out are these. So the questions will be what? Find the Fourier series coefficients of this particular x of t periodic signal. Find the Fourier series coefficients of a triangle signal. Find the Fourier series coefficients of a pulse train. Find the coefficients of periodic signal that has exponentials, like exponential, 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 and so on. A review of Euler's. E to the plus and minus j omega naught t equals cosine omega naught t plus or minus j sine omega naught t. I was talking about it in terms of x. I was using that as an x. Now, this is going to be helpful when we start doing a little bit more math on exponentials, because you see this? We are going to need to sum up all these exponentials to get our signal. But what are we going to need to find out AK? To find AK, we need to do this, right? Integrate over a complex exponential. We are going to need to do that. So it is helpful to understand some properties of what happens when you integrate over a complex exponential. So for that, let's take a look at this. Integrate over one time period. This is Euler's followed by looking at cosine omega naught t. When you integrate a cosine omega naught t over one time period, you get what? Exactly. Positive cancels out with negative, you get a 0. Can I say that same thing about sine? Yeah, sine also works the same way, right? Over one time period, it's going to be 0, right? So the area under this integration over one time period for e to the plus or minus j omega naught t is area under this guy plus or minus j under area under this guy. This equals 0, this equals 0. So use this property because we are going to need this later. Agreement on this? If I integrate over a cosine or a sine over one time period, it equals 0. Positive area cancels the negative area. Next, let us find out A2. What is A2? A2. It's a Fourier series coefficient. For what? For the second harmonic. That's why we said A2. We are going to have A0. What is A0 going to be? Okay, so here, let me ask you this. If A2 is the second harmonic, A1 is called the first or fundamental. What is A0 called? Second harmonic, fundamental frequency, A0 is what? What are we going to call A0? A line, okay, so can I, he's actually right, a line because no frequency, it's not changing, right? So DC, if DC signal, so A0 is, so a square wave could be here, could be here, could be here, could be here, right? So A0 is controlling where you are, right? So A0 is no frequency term. It's a DC term. So it's controlling where you are in terms of your height of the signal. And then the square wave itself has a particular frequency. What frequency? Give me a situation. There's a square wave. Pick a frequency. 60 hertz, right? So 60 hertz, when I multiply it by 2 pi, I get 120 pi. 120 pi radians per second. That's my omega naught. That's my fundamental, right? When I find A2, what am I finding? When I find A2, I'm finding the projection of that square wave onto the complex exponential e to the plus j k 240 pi t, right? So the projection of that signal onto the second harmonic, right? So that's the magnitude of the second harmonic component. So when I try to make up this square wave with a bunch of sinusoids, I have to pick a sinusoid of frequency 0 hertz, no frequency at all, 120 pi, 240 pi, 180 pi, 2, and keep going. Multiple of 120 pi, right? Integer multiples of 120 pi. 60 hertz is 120 pi. That's your omega naught. Once you know omega naught, then you know plus and minus omega naught, plus and minus 2 omega naught, plus and minus 3 omega naught, and so on. That's your e to the whatever function is. You're trying to project the signal onto that function. A2 will give you what is the magnitude of that sinusoid. How many sinusoids are making up my square wave? Infinite, right? Infinite sinusoids are making up my square wave. Can I make up a square wave of a frequency 60 hertz with using a sinusoid of 50 hertz? I'm trying to make a square wave of 60 hertz. Can I make it 50? I cannot use, right? So I have to, I'm limited in terms of my harmonics, right? You see that? So 0, plus and minus omega naught, plus and minus 2 omega naught, and so on. Those are the only frequencies I'm using. A2 is giving me the amplitude of the second harmonic component. How much of the second harmonic should I use? 0, finite, infinity, how much? So, oh boy, okay. All right, we are out of time. Thursday is done. So the lectures for this week are done. We are using the recitation hour, right? This Saturday, we are using the recitation hour for review. So if you guys, anybody has joined late, we have a review session Saturday, 3 p.m. in our Webex team space, the general space. You can you can come in to know the format of the exam, topics, logistics, Q&A. So we will not have like a TA recitation for this week. I will just do the review. Sound good? All right. I'm going to stop recording here. Guys, homework 6 is due tonight. Is that right? Homework 6 is due tonight. All right. Third problem of homework 6. Get it. Get it. What is that?